Welcome to part 3 of Graph Spectral Image Processing tutorial on ICIP 2020. Part 3 is going to be about image restoration. I'm Jean Chang, I'm Associate Professor in York University in Toronto, Canada. So I want to give an acknowledgement to my colleagues who supplied slides to me, Professor Wei Hu in Peking University, Enrico Magli from Politecnico di Torino, Thomas Maugey from Inria, and Antonio Ortega from the University of Southern California, and as well as many members in my lab who has kindly helped me prepare these slides. Here's the outline of today's presentation. So it's divided into two parts. I'll first talk about graph-based restoration of image and point clouds. The main focus here would be GLR. So I'll talk about GLR and why it's so important, even though it's a very simple concept, how it can be used for image denoising. Then I'll extend the notion of GLR for joint dequantization and contrast enhancement as a smart way of using GLR in that application. I'll talk about how GLR can be used for restoration or images that are not on a typical 2D grid. So the first example would be multicolored GLR for joint demosaicing and rectification of fisheye images. And then the second one would be point cloud denoising using a technique called feature GLR. And then the second half of the tutorial, I'll talk about combinations of GSP techniques and deep neural nets techniques for image restoration. I'll start by talking about deep GLR, which is a simple extension of GLR combining GSP techniques with deep neural nets, and then a recent update, which is a deep analytical graph filter using bi-orthogonal filters as a low-pass filter. We talk about deep GTV as well, more recent work that have shown it has better convergence property, and then a work from Italy, graph convolutional image denoising. So let's get started with the very basics first, which is the GLR. So Yuichi has talked about GLR in the first tutorial already, but let me just have a quick review. So GLR is X transpose LX. So given you have a graph Laplacian matrix, L equals to D minus W, where this is the degree matrix, and this is the adjacency matrix. If you say, I want to minimize X transpose LX, you're essentially saying the signal should be smooth with respect to the graph that you have defined. So this is certainly a smoothness measure. So in the case when you have a denoising problem with a very simple formation model, y equals x plus z, then you would minimize a fidelity term, minimize y minus z in L2 norm, and then with a weighting parameter, minimize the GLR as well. In this particular case, because it's an L2 norm minimization, the solution to this problem is a system of linear equations. You notice this matrix here is positive definite and sparse in general if L is sparse. So instead of inverting the matrix, which you can certainly do, you can just solve the system of linear equations using things like conjugate gradients. So the appeal of using GLR is quite strong. It's a very simple quadratic term for a fixed Laplacian. Leads to a simple L2 norm minimization in the case of denoising. And by solving a system of linear equations, which you have many methods to solve using numerical linear algebra techniques, you can solve this fairly efficiently. What I didn't really talk about is what is the appropriate graph to use to define the graph Laplacian matrix L. And previous work such as bilateral filter have looked at defining edge weights using a domain and a range filter, right? So the domain filter will be based on the location of your pixels, for example. So the two pixels are far apart. You have a small weight, which makes sense. But there's also a range filter, which is this part here. And that's based on the pixel intensities, right? So if you're trying to denoise pixels, then certainly the signal itself is the axis. And then when you want to denoise the image, the graph itself is signal dependent. So instead of writing L, as you see here, X transpose LX, it's more appropriate to write L of X, right? So then the optimization actually becomes minimize y minus x to the L2 norm plus mu x transpose LXX, right? Because the graph itself is signal dependent because the edge weight is a function of x as well. So this is a complicated optimization to solve. Then typically what you would do is you would fix L using your previous estimate of x. You solve this unconstrained quadratic programming problem, which is here. You have a new x, you update your edge weights again, and you solve it again and again. It turns out this process would promote piecewise smoothness, which is typically what you want in imaging. You can look into the details in this first reference here. We discussed this signal-dependent graph Laplacian regularization in quite a lot of detail. Yeah, so again, the emphasis here is a signal-dependent GLR, not just a GLR for a fixed graph. So it turns out using this fairly simple signal-dependent GLR, you get pretty good denoising performance already. So this is works from this first reference a few years ago already. And you can see compared to state-of-the-art denoising algorithms such as BM3D, model-based state-of-the-art denoising algorithm like BM3D, we actually do quite well. And you can see the promotion of piecewise smoothness is quite apparent when you look at the scarf, the tablecloth, and so on. We do really well compared to our competitors. This is particularly true for depth images as well, compared to BM3D. And you can see we produce very sharp edges compared to our competitors. So that was a simple use of signal-dependent GLR. We can actually use it for problems that are other than denoising. So in this case, we're looking at joint dequantization and contrast enhancement. So what is this problem? The problem is, let's say you take a picture, a JPEG, and you compress it using JPEG, and it's in low light. So you need to enhance the contrast so it's bright enough so you can see the details. But the observed information has already been quantized. So how do you overcome the quantized problem, quantization problem, as well as the contrast enhancement problem? So in this particular case, we rely on the Retinex decomposition model, which basically says for an image can be decomposed into a pixel by pixel multiplication of the reflectance and illumination, right? So this operator here means pixel by pixel multiplication. And because you're looking at a dark image, there's a scalar factor, and then there's an additive noise before you get to observation Y. So in this case, we can actually recover the luminance, the illumination and the reflectance separately, right? So you see that when we design the objective function, we have a term for the illumination, we have a term for the reflectance. They're actually variations of GLR, right? In the case of the illumination, we are, instead of just L, we have L plus L squared. So this is a generalized smoothness, very similar to a generalized total variation. This is kind of like a graph version of that, which will promote generalized smoothness instead of just regular smoothness. And then for reflectance, we have L, but in this particular case for L, we actually use negative edge weights as well, which will more strongly promote contrast or piecewise smoothness. But otherwise, it's essentially a GLR, and a GLR subject to a quantization bin constraint. T here is mapping a particular pixel patch, in this case is 10 by 10, to an 8 by 8 block, because JPEGs are encoded 8 by 8 blocks. So you're saying if I extract the 8 by 8 blocks, they have to fit inside a quantization bin. So that's the constraint. So the way we optimize this optimization is using alternating accelerated proximal gradient. Alternating here means that we're going to fix the illumination while we optimize the reflectance and vice versa. And once you fix one of these terms, then you just have a quadratic objective function with a set of constraints that are linear. And then that's essentially a convex set. So therefore, you can use a proximal gradient or the accelerated version to solve for that. You can see the details in this reference here. So you can see that some results from this paper shows that we're able to enhance the details in these dark images without enhancing the noise, right? That's the hard part. How do you enhance the details of the image without enhancing the noise? So this is our approach. This is the original image. And you can see we're able to enhance details in the image without enhancing the noise. And we do a relatively good job compared to our competitors. More images here. Again, A is the original. This is our proposal in F. And you can see that we're able to enhance the dark places without enhancing noise. The clouds here also look quite nice. More examples here. Again, we're able to enhance the flower vase, for example, and the statue that you really can't see in the original image. Modern imaging has actually evolved to beyond just regular 2D imaging. So let's look at some examples how, because we're doing a graph-based approach, these modern imaging, where you involve non-grid pixels, actually can be a very good fit. So in the first case, we're going to look at this joint demosaicing and rectification of fisheye images. So this is kind of an interesting problem. It's brought to us from an industrial partner. So if you capture a 360 image, right, using these fisheye cameras, first of all, the fisheye camera is distorted, so it looks kind of strange, as you see here. And but the fisheye cameras themselves is captured using a Bayer pattern, right, which means that you're missing color on the image sensor to begin with. So the typical pipeline would be, well, I first have a fisheye image sensor, which missing color pixels. So I would first do a demosaicing to fill in the missing color pixels first, and then I would warp the image back into proper perspective through rectification. Right? But if you think about what you're actually doing here, when you go from A to B, that's an interpolation, right? Because you're interpolating to fill in the missing color pixels, and then when you're going from the demosaic Bayer pattern grid to the rectified grid, that's another interpolation. So you're actually doing interpolation twice, and in the process, you could accumulate errors, and you could have create correlated noise, right? Because even if the noise are not correlated at the sensor, as you do interpolation, you're making the noise more correlated, which makes the problem more difficult. So a proposal is to do this joint demosaicing and rectification in one shot using graph, right? So here's an illustration. This is the original Bayer pattern grid, and this is the rectified grid. This is the proper looking image. Now for each pixel location here, when you map to the Bayer pattern grid using a reverse mapping, they typically land in the non-integer location, right? At the Bayer pattern grid, you can observe different color pixels. This is pre-demosaic, right? So you have these different color pixels at different pixel locations, right? Now what you want to do is to interpolate these missing color pixels in the rectified grid based on the color information in the Bayer pattern grid. So we formulate a problem very similar to what we saw earlier, right? This is the familiar GLR. This is the fidelity term in L2 norm. The only thing that changes is this matrix H, which help you map pixels from one grid to the other. So we assume this is fixed. Yeah, so the formulation is similar to what we had before. Now, the challenge for this particular paper is that we want to estimate the proper edge weights so that you can do interpolation. Now, the edge weights we assume is an exponential of minus the gradients, right? So if the true gradient of the two pixels between I and J is large, then the weight should be small, and vice versa. And the way we estimate the gradient between I and J, a pair of pixels I and J in the rectified grid, is to look at neighboring pixels in the Bayer pattern grid of different color, right? So if, let's say, you're interpolating red at location I and J, first of all, you can observe red gradients, such as MN here. MN is green here, but you can observe red gradients here. And so based on these observed gradients, you can compute that's one observation. You can see what is the correlation between these observed gradients and the gradients you're looking for through these weights. So these are the weights, and these are your observed gradients in different color. Then once you can estimate the gradients, the true gradients of I and J, you can do this interpolation again by solving this L2 norm, which can be solved fairly efficiently. These are some preliminary results based on our in-house database, which can be accessed here. Compared to our other approaches, some of them are doing this in 2 steps. For example, in D, they're first doing the mosaicing, and then doing the rectification using a bilinear method. And compare these two, you can clearly see that we have a much better performance. Some more results here, again, if you compare D and E, where this is the separate approach, this is the joint approach, we do better. Another example of using a graph-based approach for restoration of non-grid media data, in this case, will be point clouds. So what are point clouds? So point clouds are irregular discrete samples of 2D surface on the 3D object. So for example, you have a person, on the person you have skin, and then you have a discrete samples that are irregular. A collection of these discrete samples is called point clouds. So typically they would contain 3 locations as well as color. And it's been used for a number of applications, including VR, AR, automatic driving, drone imaging, and so on. So the many challenges with these point clouds, typically they can be acquired using active sensors, as I've shown here, and there's a huge range of pricing. And of course, at the low end of these depth sensors, you're gonna have noise. So we're focusing on the denoising problem in the next few slides, but of course there are other problems as well, such as the density of the points are either too high or too low. If it's too high, it will cause you complexity in processing them. If it's too low, it just does not render a good image. So there are problems associated with both. And then there could be missing data because of occlusion and so on. But we'll focus on the denoising problem here. When you have points in 3D space, the most important thing is to connect them in a reasonable way so that you can use graph-based processing. So what are the appropriate edge weights to assign? So this is what we're first going to talk about. Again, graph-based processing is pretty much about weighted averaging, right? So you need to average over points that you think are related, and they should be weighted averaging. Now, the signal are the coordinates, right, of these points. We want to find cleaner coordinates. So the first consideration should be, well, if points are close in 3D space, then surely they should have a large weight. They should do averaging, right? Points that are nearby are similar, so they should be averaging. So this is one consideration. The second consideration is that if things that have similar surface normals, then they should be considered similar and do different averaging. So for example, you have a tabletop and you have surface normals here. Certainly points associated with this side of the tabletop versus the other side are very different, right? You would say these points are similar, they should be aligned, whereas these points that are across different sides of the tabletop are less, they belong to different sides and they're less similar. So you want to have a pairwise measure of similarity, considering the angle difference between the surface normal seems to be reasonable. The notion of surface normal, let me talk more about this. It's very important in point cloud denoising because if we assume the point cloud is piecewise smooth, we should consider surface normals instead of the coordinates. So why is that? So first of all, what does it mean for a point cloud to be piecewise smooth? It means that the surface are piecewise smooth, right? So if a surface is completely smooth, such as this side, this is what you mean by smooth. The surface is smooth. That means all the surface normals are pointing in the same direction. then whatever penalty term or the regularization term you have in mind should be evaluated to 0, because that's what you want. You want something smooth. Now, if you consider surface normals as something that is smooth, and is piecewise smooth, then when there's a sharp discontinuity going from one side to the other side, you would have this large variation, but only occasionally, right? Most of the time it's smooth, the surface normals are the same, and occasionally you'll be large change. So what you really want is actually a piecewise smoothness with respect to the surface normals rather than the coordinates. So this is how we design our regularization term. We want to have a regularization term that is designed with respect to the surface normal. So this is what you see here. This is defined with respect to the x coordinate, but it's the same thing for the other two coordinates as well. We're saying that the signal that we're looking for, which is p, these are the coordinates. When you compute the surface normals should be smooth with respect to your graph, right? As we have defined in the previous slide using these edge weights, right? So that if the surface normals are all pointing in the same direction, right? So there's no change in surface normals, then this should evaluate to 0. Yeah, so it's very similar to the GLR that we saw before, except now we are saying, instead of the signal P, so instead of saying P transpose LP, it's small, we're saying the function N of P transpose L, N of P, it's small. So it's a function of the signal we're looking for. So this is what we mean by a feature graph Laplacian regularization, where the feature, in this case surface normal, is a function of the signal we're looking for. So this is the key difference with respect to the GR we saw a few slides ago. So when you formulate an optimization, it's still very similar. We still have a fidelity term that is saying my reconstructed coordinates should respect the noisy observations that I have. But now the GLR is a feature graph Laplacian regularization, because you're defining with respect to your surface normals, which is a function of your coordinates instead of the coordinates themselves. So the difficulty, obviously, is that we're working with normals in the regularization term instead of the coordinates. And in general, it's a nonlinear function with respect to the coordinates, which is one challenge. And the other challenge, which I talked about before, is that the Laplacian itself is a function of the coordinates, right? So not only you're talking about feature graph Laplacian regularization, actually it's also signal dependent, right? So let's talk about the first part first, the N as a function of P, right? And this is the regularization term. So how do we do that? So actually, we can do a trick where we first do a bipartite approximation of the original graph. So you divide your points into two colors, let's say red and blue. And now if you compute the surface normals of red using only neighboring blue points, as you see here, then you can actually approximate the surface normal as a function of the coordinate of P of I only, which is what you see in this equation, right? So because the blue coordinates are fixed, where you're only optimizing the red here, then by writing this approximation, where the surface normal of a point is only a linear function of its coordinates, then this guy here actually still can be written as a quadratic term, as a function of P. So that means that you can still solve a quadratic programming problem when you solve one of the two sets, assuming P here equals to 2. You're still looking at P2 norm, which is fast, right? Again, one of the appeal of GLR is that it's a quadratic term. So combined with an L2 norm fidelity term, you can solve it quickly. So we still can maintain that by doing this linear approximation. So to solve the problem of a signal dependency, all we have to do is what we did before, where we fix the graph Laplacian and solve the quadratic programming problem first. Once we have a new signal, we update the edge weights based on the definition I talked about. Then you have a new graph Laplacian, you can solve this problem again. So here are some results. You can see that our proposed approach using this signal-dependent feature graph Laplacian regularization actually provides a pretty smooth reconstruction compared to our competitors, you can see that there is piecewise smoothness. We are promoting piecewise smoothness of the structure in geometry. Same thing here. You can see our reconstruction compared to our competitors have much better piecewise smoothness in geometry. So let's switch gear a little bit and talk about deep graph spectral image restoration. So this is essentially about how we can combine GSP techniques with how we can combine GSP techniques with recent deep neural nets networks such as CNN or graph neural nets. We're focusing mostly on denoising, but I think it's not so much the application that's important, but the techniques that we're going to be talking about. So let's revisit the first GLR formulation that we talked about before, where we have an L2 norm for fidelity term, and then a smoothness prior in the form of GLR, in this case for a fixed L. And as we've talked about, one of the appeal of this formulation is in simplicity. This leads to, because it's an unconstrained quadratic programming problem in L2 norm, it leads to a system of linear equation for solution where the matrix here is sparse and positive definite. And therefore, you can solve this using conjugate gradient, for example. Of course, if you write it as the matrix inverse, you can write it in this form. And this guy here can be interpreted as a low-pass filter. So if you write it in this way, this is a interpretable filter. It's a low-pass graph filter. So this is certainly interpretable. Now, one of the questions we're asking in the beginning is, what is the appropriate graph, right? And we talk about, make a case that it should be signal dependent, which is, has been motivated by previous work, such as bilateral filter. That's interesting. But you can think of these weights that you would have that are computed based on features, in this case, the locations and the pixel values themselves, but they are kind of handcrafted features. There's no reason why these features are better than some other features, right? So one can ask the question, can we learn better features beyond the features that we're currently using? And that's essentially the basic idea of deep GLR. So instead of using handcrafted features, let's learn these features using a CNN, for example. And then once we have these notion of features for each pixel, so these are features corresponding to pixel I and pixel J, you compute a notion of feature distance. And then the notion of feature distance is used to compute the edge weights. In particular, the edge weight is exponential or minus the feature distance. So the feature distance is large, you have a small edge weight, and vice versa. But then we still do the rest of the step exactly the same. So we're still gonna, once you construct the graph L, you can still formulate a optimization problem that minimize the L2 norm, L2 norm for your fidelity term, your regularization term. Use the QP solver to solve it, and you can still reconstruct the image. So these are the CNN we use for different parameters. We actually do a pre-filtering of the image first, and we also optimize the weighting parameter mu. And this is the network that we use to learn features for individual pixels. We can actually do this a number of times, kind of like unrolling. There's been work on unrolling of a sparse coding, for example, and we can do something similar. So what's the advantage, you might ask? What's the advantage of doing this this way, where we still maintain a graph formulation and we just learn the features? Well, one advantage is that we can guarantee the numerical stability of our solution. What do I mean by that? So the solution is a system of linear equations, as I've shown here. A system of linear equations, the stability of the system, of this linear system, depends on the conditioning number of this matrix, right? Which is the the ratio between the largest to the smallest eigenvalue. So it turns out that, as proven in this paper, that if you construct a graph that have a bounded degree, then the conditioning number can be easily bounded through Gershwin-Circles theorem. And therefore, you can guarantee the stability of this linear system no matter what features are being learned. So this is great when you want to achieve some kind of robustness to learning. Let's say you don't have enough data, or the data is of different types than the actual testing data, then this will come in handy. So I'll talk about that next. If you look at the experiments, you can see that in the case when you're training on Gaussian noise and you're testing on Gaussian noise, the performance of our approach compared to state of the art in NewNet CDNN, DNCNN, it's one of the state of the art NewNet approach to image denoising. We do relatively well. There's not a huge difference in PSNR. Now, when you're actually training on Gaussian noise and then testing on low light images, so there's a mismatch in statistics between your training data and your testing data. You can see that our approach is much more robust, right? You can see the PSNR numbers that we have compared to this CDN, CNN, we know significantly better. So this is one of the advantage of combining a model-based approach with a learning approach, where because we can guarantee certain aspects of our design, in this case, the numerical stability of our solution, we're able to achieve more robust learning. Here are some results that actually demonstrate this. Visually, this is again training on Gaussian noise and testing on low light images. We can see that we do much better than our competitor in visual quality as well. Here's just another visual example where you see it's quite clear that visually we do much better. So there's been some more recent work along this line. If you look at the system linear equations that we have from the minimization of L2, L2 norm, this guy here is essentially a low pass filter, right? So this is equals to X star equals to I plus mu L inverse Y. So this is essentially a low pass filter. Now to get to this solution, you don't need to do a matrix inverse. Again, you can just use, for example, a conjugate gradient. You can solve this equation fairly quickly. But the issue here is that that's still complex. That's hard to compute. So if the goal is some kind of a low pass filter with respect to some graph, can we do filtering faster than solving the system linear equations? So it turns out you can, and we're using GraphBio, which is an analytical graph filter. In this case, it's actually a biorthogonal graph wavelets that is has perfect reconstruction condition. And to implement this, you can use a Chebyshев approximation, and therefore can be run very fast because each pixels can be cleaned or interpolated using a neighboring pixels. Assuming you have nth order polynomial, it's just an nth neighborhood. Right? And the advantage, just like the previous case, is that you have an interpretable filter, right? We know it's a graph low pass filter, right? This is unlike typical CNN approach where you learn the filter coefficients for a particular convolutional layer, but you have no idea what the filter is doing. Here we know it's a low pass graph filter with a no filtering response. So this is nice. One of the downfall of GraphBio is that it only applies to bipartite graph. So when we're dealing with images, we have to divide the grid into these two grid pattern, and then we process them separately before we put things back together. So that's kind of the only caveats. You can see in this case that if there's a statistical mismatch between training and testing, again, we do better than the comparable DNCNN parts. So the PSNR is a little bit better. One of the advantages that I didn't mention up till now is that using this approach, because we're only learning features, right? We're never going to learn filter coefficients. We're able to learn much fewer number of parameters, right? So implementationally, it's much smaller because the number of parameters you need to store, it's much smaller. And then training will be a lot easier as well because you're training much fewer percentage of parameters in the neural net. Yet another iteration of this is using deep graph TV. So if you look at the formulation, so instead of using GLR, which is X transpose LX or X transpose LXX, if you're looking at the signal dependent version, you can actually minimize the L1 norm instead of the L2 norm, right? So in this case, it's graph TV, defined as the weighted sum of these connected pixel pair of I and J. But in this case, you're looking at the L1 norm instead of the L2 norm, right? So what is the difference of using GTV instead of GLR? So it has been shown in one of these papers, reference 2 here, that actually, even though both promote piecewise smoothness, and again, we're talking about the signal-dependent graph Laplacian regularization, right? It's not just GLR, it's signal-dependent graph Laplacian regularization. And we're comparing that with signal-dependent graph TV. So when you're comparing these two, has been shown that actually the signal-dependent graph TV promote piecewise smoothness much faster than the signal-dependent GLR. Okay, so this is a nice thing to know. That it promotes piecewise smoothness faster in terms of convergence. Now, the problem with this formulation is that now you have the L1 norm combined with an L2 norm, right? So L1 norm, it's convex but non-smooth. So minimizing this is not as easy as what we've done before. Now you can use proximal gradient type optimization techniques to solve this, but that's fairly complex. So what we did is actually a very simple trick. Basically, we define a new Laplacian called the L1 Laplacian, which is the original weight, essentially divided by xi minus xj absolute value. So what that means is that when you multiply this guy out, you actually have a factor here on the bottom that when you, you can write it as a L2 norm so that you have a square. So you have this new weights. And because of this weights in the bottom, it cancels out one of these squares, and therefore it's actually a L1 norm, right? So by smartly defining this L1 Laplacian, we can nonetheless write this L1 norm as a fake L2 norm. Yeah, but you're still minimizing an L2 norm and L2 norm, and you can still solve this as a system of linear equations, and you can still interpret this as a low-pass filter, right? So it's a still interpretable low-pass graph filter. So this is nice. And because we can interpret this as a low-pass graph filter, we know what the desired filter response should be. And therefore, instead of doing this, we can actually have a fast implementation through a Lanczos approximation. So this is the equation that actually approximates the filter response. So it's talked about here in the second reference. But essentially, it's a fast implementation of a graph filter, given that you know what the filter response is. And again, because we can interpret the filter as a graph low-pass filter, we know what this filter response is. We can therefore apply this Lanczos approximation and solve this very quickly. The results are somewhat similar to what I've shown before. In this case, you train on Gaussian noise and you test on actually capture noisy images, where the database actually provide both clean and actual capture noisy images, so we can compute PSNR. We do better than DNCNN in terms of PSNR, and you can see quite clearly that visual performance is also better. My student implementation in this case actually use even fewer parameters than the previous implementation. Compared to DNCNN, we actually save up to 80% of the parameters. So your CNN is significantly smaller than what you started off with DNCNN. Lastly, I'll talk about this work from Enrico's lab in Italy. I'll just briefly talk about this. So every denoising algorithm I talked about so far is done locally, right? It just you look at the similarity with its local pixels and you do some kind of weighted average based on your design in your graph. But actually, one of the strong priors that has been discovered to work in image processing, in image denoising, it's non-local self-similarity, right? So this non-local self-similarity has been shown to work really well. And so this is described in this paper. Enrico and his colleague has shown that if you design the graph smartly, you can actually take account of a non-local similarity as well. So here's the network design. And here's the operator in each of these layers. So I won't go into detail in this presentation, but essentially they're able to design a very smartly connected network where you can do filtering both locally and locally. So you have patches that are similar across the image. You can account for that as well. And the performance is fantastic. So you compare the denoising performance with DNCNN, this is quite a significant gain. And for piecewise smooth images such as depth maps, this is the technique that I talked about in the beginning of the presentation using signal-dependent GLR. There's a significant gain here. So let me conclude. The driving observation here, and this motivates why I'm doing the tutorial, is that graph is really a very flexible abstraction that describe pairwise similarity. And you can estimate these pairwise similarity locally just by looking at 2 pixels, either through a notion of correlation, you think about it statistically, or the similarity is defined with respect to a feature distance. So you have some feature vector, either learn or use something that is pre-selected. Once you have a notion of feature distance, you can define similarity, then you can construct a graph. So it's a very flexible way of describing the relationships among the samples. Graph can be also used as a way to express domain knowledge. So if you know a priori which nodes are similar to which one based on a particular domain, this is a convenient way of expressing this domain knowledge. Because we're using graph, and based on the graph signal processing theory that we have, we can actually interpret these interpolation methods, denoising methods, as filters, as graph filters. So it provides interpretability of your operations, right? And this is different from typical CNN, where when you learn a filter, you have no idea what the filter coefficients are doing. And so it makes these convolutional filters hard to interpret. In our case, we can always interpret our formulated problem, our operations, as graph low-pass filters, which is great. And then this interpretability actually leads to actual useful things, right? So, for example, it can lead to fast or simple implementations that either require fewer number of parameters or fast implementation, leveraging on things we know in spectral graph theory, numerical linear algebra, and convex optimization. So I'm making a case here that machine learning is great, and we should combine tools in machine learning in our approach. But graph as an abstraction is also great. It provides way of embedding domain knowledge. It provides interpretability, and in many cases, it can also lead to faster or simpler implementation. Actually, a lot of these ideas are discussed in this recent paper by Professor Pascal Frossard and his colleague in EPFL. So I'm in some way rehashing the main ideas in that paper. So this concludes the end of part 3 of the tutorial. Here are my contact info. If you have any questions about this tutorial, please feel free to contact me through email. Thank you.